Well, let's talk about the neurotransmitters. Neurotransmitters, remember, are paracrine in nature. They do not make full contact. I should say the axon terminal of the presynaptic cell does not make full contact typically with the postsynaptic cell. So when the neurotransmitters are released, they cross the synaptic cleft and bind with their neighboring cell. In a paracrine fashion, they bind the receptors. So I've had people ask me, well, how many neurotransmitters are there? And it's a kind of a bizarre question because there really are hundreds of them and many that we are identifying every day. But most people just know the catchy ones. They know serotonin, they know dopamine, they might know epinephrine. I doubt they know norepinephrine. They probably don't know melatonin is a neurotransmitter. So here's a list of some of the most popular neurotransmitters. They're organized by their chemical structures pretty much. But you can see over on the top over here, you have these things called amines. Okay, and it's just a chemical structure. That's what it's all about. And a particular type of amine, quaternary amine, is where acetylcholine fits. Okay, and that's interesting. I'm going to jump down here. We got amino acids and modified amino acids. That's where GABA is, and glutamate, and glycine, and histamine. And then we have these neuropeptides and enkephalins, endorphins we've talked about. We have peptide hormones like oxytocin that we'll talk about at the end of this lecture. Substance P, CCK, vasopressin, all these, right? And then we have all these hypothalamic releasing hormones. I'm not sure why there's only 3 here. There should be 7 here. So GnRH, thyroid releasing hormone. So, and then of course we have fat-based hormones. Anandamide we talked about is a agonist. I should say cannabis is an agonist for anandamide. Anandamide is the natural cannabinoid in the system. And of course, some neurotransmitters are gases like nitric oxide. So generally, this is an organized structure of them. I don't really, it doesn't matter to me that you know the structure. What I want you to focus on right now is this right here, this area called the monoamines. The monoamines are subdivided into catecholamines and indolamines. Okay? And look what's in this category. Within the catecholamines, we have epinephrine, norepinephrine, dopamine, and within the indolamines, we have serotonin and melatonin. So all of these 5 neurotransmitters are all considered monoamines. Okay, and that's going to play into what I'm getting to next. Okay, because prior to the discovery of Prozac, we used a drug called monoamine oxidase inhibitor. Okay, now we got to go back to our synapse concept on this. So the neurotransmitter is released into the synapse, and then it binds the protein receptor, creates an iPSP or an EPSP, and then when it's done, it's recycled. It breaks off and it goes back, and it needs to be taken back up into the cell. And one way it is taken back up into the cell is via enzymes. Enzymes break it down so that it can be broken, so it can be brought back into the cell and then put together in the cell and get ready to use again. That's the way it works with acetylcholine. There's an enzyme called acetylcholinesterase that breaks down acetylcholine into acetyl and choline. Both parts are reuptaken into the cell and then they're put back together ready to use again. Well, the monoamines are similar. The enzyme for monoamines is monoamine oxidase. Okay? And that breaks down and helps the recycling of these neurotransmitters. Well, we stumbled on a drug called monoamine oxidase inhibitor, and it was effective in treating depression. The problem is it had major side effects. The major side effects were death if you ate the wrong food. So it was a last choice sort of mechanism. That takes us to where we are today with the treatment of depression and Prozac. So let's see how Prozac works. So as I said before, here is the axon terminal of the presynaptic cell releasing serotonin into the synaptic cleft. It comes across the cleft, it binds its receptor, and it creates an iPSP or an EPSP. That's what it does. When it's done, it unbinds and comes back in and is taken back up. Sometimes it's broken down by an enzyme like I talked about earlier. Sometimes it's just taken right back up whole. And that's what happens to serotonin. And this is called a transporter, a reuptake transporter. It's being reuptaken into the cell, right? So along comes Prozac right here, which blocks the transporter. It is a selective serotonin reuptake inhibitor, an SSRI. That's what it does. It prevents serotonin from going back into the cell. So what does it do? It comes back and it binds again. And so you end up getting more bang for your buck out of the serotonin that's released. Now, the MAO inhibitors work in a similar fashion. They break down or prevent the breakdown of the neurotransmitters, prevent them to be taken back up into the cell. And so you have a little bit of the same effect. But here's the kicker. Prozac affects this. MAO inhibitors affect all 5 of these. All 5. So if we were in class, I would try to get you to decide what's the difference between those two. But since we're in this interesting semester that we have, I'll cut to the chase. If you are affecting 5 neurotransmitters to get the job done instead of 1, you're going to end up with a lot more side effects. That's why Prozac has been such a boon. Okay, Prozac seems to do as good a job, if not better, than MAO inhibitors by affecting only 1 neurotransmitter. And that means also limited side effects. So I really want you to grasp the concept between how Prozac works and how MAO inhibitors work. Prozac works on 1 neurotransmitter. MAO inhibitors work on all 5. And the difference is MAO inhibitors are a sloppy drug, and they end up with more side effects, and of course, the most lethal of all side effects, which is death.